So I'm going to give an idiosyncratic explanation of basic mathematical induction. Rather than tell you how to do induction, I'm going to try to motivate why it is the way it is. And so hopefully there's somebody out there where this will be the thing that makes it click. And I got to say, mathematical induction, once you understand the insight, is quite easy, but before you understand the insight, seems mystical. And so there are all these things, one of the things that we're going to say at some point is assume that in order to prove something is true. And it's like, well, why can you assume that? What's going on here? And so I want to kind of motivate where that comes from. Okay, so we're going to work with the standard mathematical function, which I'm going to call S of n, which is just going to be the sum of the first n integers. So for instance, if you give me S of 2, then I want the sum of the first two integers, so that's 1 plus 2, which is equal to 3. If you say S of 4, then I want the sum of the first four integers, 1 plus 2 plus 3 plus 4, which is equal to 10. S of 5 is the sum of the first five integers, 1 plus 2 plus 3 plus 4 plus 5, which is equal to 15, right? And the thing about this is I'd like to have a formula that doesn't require me to compute each time all of these things. So like, what is S of a million? That's a rather big number, and I really don't want to do 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 to calculate it. That's going to be really annoying. So what I'd like is some other function that can calculate this in a much quicker way rather than adding up all those numbers manually. And it turns out there is such a function. And so the function, I'm going to give it a name, f of n. And this function is you take whatever the value of n is, you multiply it by 1 more than n, and then you divide the whole result by 2. And what I'm going to prove using induction is that S of n, whatever that value, 1 plus 2 plus 3 plus 4 plus 5 all the way up to n, is actually equal to f of n. So you can use this function as a fast way of computing that one. But this requires a proof, right? Because this function does not look anything like 1 plus 2 plus 3 plus 4 plus 5. And so you need some reason to believe that calculating this thing over here on the right, this f of n, is actually going to calculate the sum of the first n numbers. And so what we're going to do is we're going to just start brute force checking this. And then what we're going to notice is that our way of brute force checking this can be sort of simplified or maybe generalized. And that generalization is going to be our proof by induction. So let's start brute force checking. And this, I'm going to calculate both S of n and f of n and check, are they the same? So my S of n calculation will be here, my f of n calculation will be here, and are they the same? The same will be over here. And so S of 1 was just equal to 1. Maybe we'll fill in a few values really quickly here. S of 2 is 1 plus 2, which is 3. S of 3 is 1 plus 2 plus 3, which is 6. S of 4 is 1 plus 2 plus 3 plus 4, which is 10. S of 5 is 1 plus 2 plus 3 plus 4 plus 5, which is 15. I'm already getting annoyed, right? Maybe we'll do one more. S of 6 is 1 plus 2 plus 3 plus 4 plus 5 plus 6. Whoops, that's not a thing, that's fine, equals 21, right? And so lost all of that, plus 6 equals, there we go. And now let's check the f of n's. And remember, f of n is n times n plus 1 over 2. So f of 1 is 1 times 1 plus 1 over 2, which is equal to 2 divided by 2, which is indeed 1. So we definitely have this value and this value are equal, and so they are the same. Now we can check s of 2, say f of 2 is equal to 2 times 2 plus 1 over 2. So 2 times 3 is 6, divided by 2 is 3. 3 and 3 are the same, so s of 2 and f of 2 are the same. So that checks out. Next one, f of 3 is equal to 3 times 3 plus 1 over 2. So this is 3 times 4, which is 12, divided by 2 is 6. 6 and 6 are the same. Checks out. F of 4 is equal to 4 times 4 plus 1 over 2. So this is 5 times 4 is 20. 20 divided by 2 is in fact 10. 10 is equal to 10, so those things are the same. F of 5, it's probably overkill at this point. 5 times 5 plus 1 over 2, that's 6. Divided by 2 times 5 is 3 times 5 is 15. Checks out, those are the same, etc. Okay, so this is already getting a little tedious. Let's pretend, though, that I decided to do some work for you. And I've already calculated up to s of 100. And I actually wrote the whole thing down, this whole table, and plus, I'm going to use some dots here, plus 99, plus 100, and I found that when you add all of that up, you get 5,050. And over here, we also checked f of 100, which is equal to 100 times 100 plus 1 divided by 2, which is equal to 5,050. Okay, and so those checked out. And now I ask you, can you please calculate or check this for s of 101 and f of 101? So f of 101 is easy to calculate, right? You're just going to put 101 times 101 plus 1 divided by 2. You can throw that into a calculator quickly, and you will get that thing is equal to, I can't think today, 5151, right? Okay. But what we'd like to do is also calculate s of 101. And in order to do, because we need to check, does s of 101 equal 5,151? So you could sit there and calculate 1 plus 2 plus 3 plus 4 plus ... plus 99 plus 100 plus 101 and see what it's equal to. Plug all of that into your calculator. It would take a while, right? Or you can be a little smart. You can say, hey, I'm going to assume you weren't lying, Internet YouTube guy. That s of 100 is equal to f of 100, right? Actually, we've already calculated these, so maybe before that, let me back up a step. Let's just, yeah, that's actually fine. Okay, s of 100 is equal to f of 100. We actually don't need that. I'm going to assume you weren't lying to me. This is my first version of this, that s of 100 is equal to 5,050, right? And so instead of doing all the work of calculating this, so this is s of 101, the whole thing, out to here, But if I just look at the first 100, that's S of 100. And you've already told me that that is 5,050. And so now all I got to do is add 101 to that to get 5151. Right? And now I can quickly see that that thing and that thing are equal. And so assuming you didn't lie to me about the value of this part, I'm happy again. I've now shown it for S of 101. Okay. But here we're still using actual values that we calculated. Like I calculated this side for you, right? And you were using that value. Let's take this even a step further. Okay, so let me move up here. Let's say I've calculated it all the way to S of 1,000. And I tell you, I promise, S of 1,000 equals F of 1,000. Checks out. But unlike before, I don't tell you what this is equal to. I don't say, hey, S of 1,000 is some value. I just say, look, I've checked all the numbers up to n equal to 1,000. And I know that for every number S of k, it's equal to F of k for k from 1 up to 1,000. Already checked it. And then I say to you, hey, can you please check that S of 1,001 equals F of 1,001. And so you're going to look at this and you're going to say, okay, S of 1,001, well, that's equal to 1 plus 2 plus ... plus 999 plus 1,000 plus 1,001. You're going to look at this and be like, no, thank you. I don't want to calculate that thing. It's going to take me forever. But then we could use our clever trick again. It's like, well, what is this? This is just S of 1,000. And so what do I know? I know S of 1,001 is equal to S of 1,000 plus 1,001. And now, assuming you're not lying to me, assuming weird internet guy, you are not lying, then you said S of 1,000 is equal to F of 1,000. So that means I can take this whole expression and say, well, I know, assuming you're not lying to me, S of 1,000 is S of 1,001 has to be equal to F of 1,000 plus 1,001, and this thing's not so bad to calculate because that's just 1,000 times 1,000 plus 1 divided by 2, and then that's substituting there, right? And then bring the 1,001 down. This thing turns into 500. So let's do a little quick. I'm dividing the 2 through, so it's 1,001 over here, and so we get 500,500 plus 1,001, and that is equal to 501,501. So now I know what the value of S of 1,001 is. It's this, as long as I was allowed to make that shift. So I have to assume that you haven't lied to me. I have to assume that I can replace the hard to calculate thing with the easy to calculate thing. But if you didn't lie to me, I got to do a much easier computation to calculate what that next one is. And now I can easily check whether that's equal to F of 1,001. Because this is just 1,001 times 1,001 plus 2 over 2. And you plug that into your calculator and you get that, yes, that is equal to that. And so it checks out again. So now what I've done is I've said, you know, assuming you didn't lie, that S of 1,000 equals F of 1,000, then I've checked that S of 1001 is equal to F of 1001. So that checks out, right? And we could do the same thing up to, much bigger numbers. So let's say I tell you that I've actually checked the first million, and it really happens to be the case that S of 1,000,000 is equal to F of 1,000,000, and I ask you, is S of 1,000,001 equal to F of 1,000,001? And here we do the same process. You'd say, well, S of 1,000,001 is equal to 1 plus 2 plus all the way up to 999,999 plus 1,000,000. Get enough zeros in there. One more plus 1,000,001, right? And this is you're never going to plug all of these into your calculator, so you're definitely going to have to use this trick. You're going to say, well, I'm just going to go on the assumption that you haven't lied to me, that this is true, because this whole piece here is S of 1,000,000, and if you haven't lied to me, I can swap that out with F of 1,000,000. So this is F of 1,000,000 plus 1,000,001, and so this thing I can calculate. This is 1,000,000 times 1,000,000 plus 1, which I'm just going to go ahead and write as 1,000,001 divided by 2. That thing I can calculate. That is, I've got it here to shorten this a little bit. That is 500 trillion 1 billion, or 500 trillion 500 million. Big number at that point. Definitely didn't want to count that up, right? Plus 1,000,001, so I get 500 trillion 1 billion 500 million and 1, right? So that's this value, assuming you haven't lied to me that I'm allowed to make this switch. And now I can easily calculate the, little bit of math necessary to do this. That's just 1,000,001 times 1,000,002, or 2 divided by 1, 2, 3, 4, 5, 2 divided by 2, which I can calculate, throw it into my calculator, and it really does equal this 500 trillion 1 billion 500 million. I messed something up somewhere. There should be some more zeros in here. So whatever it is, the point is not the value. You can check me on the values. The point is, assuming I can make this switch, then I can use that switch to calculate the left-hand side of the thing that I'm trying to test, S of whatever. And the right-hand side is pretty easy, F of whatever, and check that the next one. And so now we want to turn this into a Mad Lib, because what I did here for 1,000,000 was exactly the same as what I had done before for 1,000, right? It's the same process. So what I really want to do is say, hey, assume you know, or haven't lied to me if you prefer, that S of k, for some k, is equal to F of k. So k here could be 1,000, it could be 1,000,000, it could be 1,000,000,000, it's whatever. Assume I already know that. I want to just show that S of k plus 1 is equal to F of k. And so this is where this assumption business with inductive proofs comes in. It's like, really what I've got is a pattern of proof. It's a pattern of proof that always if I assume you haven't lied to me up to any particular value, then I can use that assumption to speed check the next value. That's what we're doing. And the point is that this, if I can do it in this general kind of Mad Lib form, k plus 1. If I can do it in this general Mad Lib form, then it works for all the values as long as there's at least one value that you really haven't lied to me on, that you've really told me about. And then I can get all the other ones by repeatedly applying this same argument, right? So this is the idea. So let's look at this thing. It's like, okay, well, we want to check, does S of k plus 1 equal f of k plus 1? So we do it exactly like we did before. Well, what's that? That's 1 plus 2 plus ... plus k plus 1. We recognize that this thing here is really the same as S of k. And now we say, well, I'm going to assume that you didn't lie to me, that S of k is equal to f of k. So I'm going to swap that out. F of k plus k plus 1. Right? But now I need to, I don't have a value here. I have an equation here. So this is the other big change in generalizing it. So this is equal to k times k plus 1 over 2. That's what f of k becomes. And then we still add the k plus 1 over here. And so now what I'm going to do is I'm just going to multiply it through. So this is k squared plus k divided by 2. And I might as well multiply this by 2 over 2. Multiply by 1 to simplify everything. So this is plus 2k plus 2 over 2 so that I can simplify these. So the whole thing is k squared plus 3k plus 2 over 2. So that gives me a formula for S of the left-hand side of what I'm trying to check. I'm trying to see if these things are the same, right? And I used that same trick. Assuming you didn't lie to me, I swapped out S of k for f of k, and I've derived a kind of result, algebraic expression from that. And so now what I'm going to do is I'm going to check the other side. So what's f of k plus 1? Because that's the thing I want to know, is that equal to f of k plus 1? And so this is now k plus 1 times k plus 1 plus 1, which is k plus 2 over 2. And I'm going to multiply this through. So k squared plus a k plus a 2k plus 2 over 2, just multiplying through. And that thing is then k squared plus 3k plus 2 over 2. And look at that. Those two expressions are the same. So what we've shown is that S of k plus 1 is equal to f of k plus 1 under the assumption that I could make this swap. So it was like, assuming, again, I know I'm harping on this, but assuming you didn't lie to me that this is true, this also has to be true. Okay. And now the final claim is that this actually proves it for everything. And the reason is we know that S of 1 is equal to 1 and f of 1 is equal to 1. We checked that way back at the beginning. And so we know at the very beginning S of 1 is equal to f of 1, right? And so I don't actually have to assume that this is true. I just know it's true, right? And so because I know it's true, I know you didn't lie to me that when k is equal to 1, S of 1 is equal to 1. But that means that my little proof structure here says that, well, you're not lying to me that S of 1 is equal to f of 1, so it has to be the case that S of 2 is equal to f of 2, because my proof structure says when you haven't lied to me about the k cases, it also has to be true for the k plus 1 case. But now I know you haven't lied to me about the 2 case. So now I know it's also true for the 2 plus 1 case. So S of 3 is equal to f of 3. But now I know you haven't lied to me about the 3 case. So, when k is 3, then I can apply this same argument and I get for free that S of 4 is equal to f of 4, etc. In other words, this general, if you didn't lie to me on the last case, then I also know the next case, right? This general form, plus the fact that I have a starting point where I know you didn't lie, means that I've got them all. I know that S of 1 is equal to F of 1, and then by the argument, this implies S, so maybe I use implication, S of 2 equals F of 2 implies S of 3 is equal to F of 3 implies all the way up for every number you want. So this is, I'm not going to, you should go and learn the steps of induction. Go learn how to write an inductive proof. So you need a base case, you need to prove the assuming it's true for the case K, proving it's true for case K plus 1. All of that, there are plenty of good videos out there for. The purpose of this video was really to show you where that assumption is coming from. That it's not coming out of the blue. It's like building a Mad Lib version of just doing every single case by hand and using the previous case to simplify it. That's all induction is. And it's making it easier and more mechanical to do it quickly. So, hope this helps.